Hello, welcome everyone. This is the first lesson of the complete guide to the reinforced concrete design as per ESEN and the Eurocode. This is the second level. You know, the first level was delivered in class, and we hope that we will prepare the online part in very soon after this second level is completed. So let's directly go to the course content. This is the first chapter will cover the basic design concepts. This chapter was covered in the first lesson. Again, we will cover it here because of its importance, as it is the door to the reinforced concrete designs. Okay, this is on the second level. Again, this is the revision that was done for the chapter that was done in the first level. We will revise it so that you have the basics of RC beam designs. These are the straight beam designs, and we will see how to design them for flexure and for shear. In the third chapter, we will design curved beams in plan. Okay, so curved beams may be used for different reasons, so we are going to see what makes it different from the straight beams that we are going to cover in the second chapter. We will do the manual calculations as well as with the use of Excel templates. Okay, on the fourth chapter, we will design isolated footings. Isolated footing means footings that are going to support or that support a single column on it. So again, here we will calculate it. We will calculate everything, the dimensions, the reinforcements, everything with manual calculations. Then we will use Excel templates and we will check them. On the fifth chapter, we will cover the design of combined footings. Again, we will do it. These combined footings are footings that are supporting two columns, and we will design them with a manual, and finally we will check them with Excels that we developed it. Okay, the sixth chapter will cover the RC columns. This can be rectangular or circular. Both of them will be explained, and we will see illustrative examples in this sixth chapter. Finally, we will cover bar bending, cutting, and detailing of each element while we are learning in the chapter. I mean, in the fourth chapter, when we are learning isolated footing, we will learn how the bars are cut, how the bars are bent, and how the detailing is done when we are doing each structural member that we are going to design. Well, let's go to the first chapter, that is the revision on the basic design concepts. Here we will have 4 subtopics. The first topic will be introduction to the reinforced concrete. Here we will discuss how this reinforced concrete is going to be formed, and the second part we will discuss structure load response, and this subtopic is very crucial and each one of you must clearly understand it. If not, you may ask questions as you need. I hope you will understand it clearly at the end of this lesson. In the third topic, we will cover why this reinforced concrete is so crucial to use. Okay, what makes it different from other materials that are available on earth. In the fourth part, we will cover how materials are specified in ESEN as well as in the Eurocode, and how we use them in the design calculations. Okay, so these are the 4 topics, and we will go straight to the first part, that is the introduction to the reinforced concrete. Okay, as we know, reinforced concrete is simply the reinforcement added to the concrete. So we had a concrete, then due to some weaknesses in the concrete, when we add the reinforcement to strengthen it, we get a reinforced concrete. So what's concrete by itself? Concrete by itself, it is just a mix of these following materials. The first material will be aggregate, which is composed of these 2 parts. The fine aggregate, that we call them sometimes sand, where the size particle varies from this size 0.074 mm to 4.7 mm. Okay, and we have also the coarse aggregate, where the size varies from this 4.75 to 75 millimeter. So this is the aggregate that are one component of the concrete. When this aggregate is mixed with cement, and we add some water on it as required, and sometimes we may add admixtures to alter or to change some of its properties. Okay, so basically concrete is the mixture of these three. However, admixtures may be added as required. Okay, as required. So for this reason, the mixture of these materials will give us the final product, that is the concrete. So when this concrete is, you mix it with this reinforcement, however, this must be clearly known that we are not simply putting reinforcement inside concrete. We are putting it systematically where the reinforcement is required and in an arrangement that is systematic and a scientific way. Okay, so this reinforcement added to the concrete in a systematic way will give us reinforced concrete. Well, before going to the second part of this chapter, I would like to remind you that there are elements that affect the property of the concrete, such as the water cement ratio, the curing period, and the cement content, and the quality of the aggregate that are used, and so on. Okay, so these parameters affect the quality of the concrete. Well, this reinforcement is already manufactured in industries and it comes prepared, so we will have higher impact and we have higher responsibility to deal with this one. Okay, just these elements will be tested such that it satisfies the required strength. Okay, in the second part of this video of this lesson, we are going to deal with the structural load response. What do we mean by that? There is a structure. When a load acts on this structure responds in a certain way. These three elements, or these three concepts, are highly interrelated, so that the engineer is required to know each one's property. Okay, and so that finally the design that will be provided will satisfy and will predict and be safe against the future response of the structure. Okay, now let's deal with them one by one. What's structure exactly? Structure is simply an interconnected members, okay, that are, if I summarize the definition, we can say it's a member that supports load and that can transfer load to the other members, and that's in equilibrium and unstable. Okay, simple. These characteristics are satisfied by this structure. So a structural member is a member that can support load, transfer load, and be stable under the different loading combinations. Okay, so this is a structure is defined as a system of interconnected members assembled in a stable configuration and used to support load or combination of loads. So some samples of the beam of the structure can be beams, columns, slab, wall, footing, and so on. Okay, so let me take this as an example. This is simply supported element, or you can take the walls, the columns, the slab, and so on here. Okay, these are what you call structural members. So the interconnection of these elements are called structure, where each one is called a structural member or a structural element. Okay, so the force or the load is just a force, actions that produce stresses, deformations, or accelerations or decelerations. Okay, so this is loads. This can be made by force or an output of a force that we may call it couple or a moment. Okay, well, for example, this wall, this partition wall that's acting on this beam, okay, maybe described as a wall, as a load. Okay, as a load. So there is a structure that's the beam, and there's a load or a force that's acting on this structural member. Then finally there's a response. When there is the load, so the beam will respond to the load in a certain way. So in terms of internal stresses, in terms of deformations, maybe cracks, all these things will be how the element will respond to the loading that was above it. Okay, that was over it here. Now, key concepts that you need to consider when you are designing members. Okay, the structural member, the type of the structure, is it column, beam, what makes an element a column, and what makes it a beam. Okay, depending on whether the load is acting in what direction, and whether it is a flexural member or whether it is a compression member. These elements, this type of structure will guide you to the proper design of the element, because column will be designed slightly in a different way than the beam, which will be designed in a different way than the slab. Each element must be known. The material type, whether it's reinforced concrete or other type of materials. The size of the structure must be also considered, must be taken into consideration. The arrangement of the structure, whether it is vertical, horizontal, inclined, and so on, whether it's circular or what. Okay, all these elements must be taken into consideration when the designer is designing the structural member. There's a boundary condition, also the support type, the support arrangement, and so on. Okay, these key points must be known by the designer so that you properly design the element. Okay, there's a load. So in the load, these load types, is it dead load, live load, and so on. Knowing whether it is dead load or live load or earthquake will also affect the factor of safety that are related with these types of loads. For example, the dead load may be associated with 1.35 for the dead load, maybe live load 1.5. So knowing the type of load here will make you estimate or predict how the structure will respond in the future. Earthquakes are lateral loads, wind load are lateral loads. These are generally gravitational loads, downward loads. Okay, so this will tell us, will allow us know how the element will respond in the future. The arrangement of the load, whether it's concentrated load or line load, and so on. Okay, and the direction of the load, is it vertical or lateral, such as the one that we have discussed here. The magnitude of the load, if it's large or small, and so on. The load cases and the load combinations, which load will they act simultaneously or not, and other factors. All these were discussed in detail in the first level. So the response will be in terms of deformations and internal stress. Always the engineer must make sure that this stress and deformations should be within the allowable limits. These are guided by the code. Okay, so we will specify, we will make sure that the limits should not be exceeded. Now let's see some representations. Okay, there was here a beam. This beam is acted upon by a load. So there is a structure or a structural member, and there is a load. So due to this load, this member is expected to deform like this. And due to this deformation, this is a response. This response can result in certain cracks, maybe flexural cracks somewhere here, maybe shear cracks around the support, and so on. So once we know such kind of cracks or problems may occur, we as a designers, we know where the enemy is going to attack. So for this, we need to provide reinforcements that are required to resist this kind of possible future failures. Okay, so that's why it's important to know the structural load responses relationship. Okay, for example, you have such kind of continuous beam of these two spans. So when you have such kind of loading, this is the structure, this is the load, and due to the loading system, it will deform like this. So we expect that the concrete is weak somewhere in the tension zone, so we will have such kind of possible cracks in the tension zone at the bottom, and around here at the top, because there will be tension will be at the top here, there is possibility of cracks at the top, and we are expecting shear cracks, inclined shear cracks around maybe the supports. Okay, so once we know these possible future failures due to the loading conditions, then we are able to design the element to be safe. Now, for example, again, if we take this isolated footing, due to the load, there will be surely a pressure in the soil. Now, due to this load, the element is expected to deform in such a way, because the soil is not, as we assume in some of the software analysis, to be fixed support, but this one is a kind of elastic member. Okay, at the bottom. Okay, the soil will deform like this. So due to this, we are expecting that the bottom part will have or will suffer certain cracks. So that's why you most of the time see reinforcement in the isolated footing to be around the bottom and opens upward like this. Okay, so in addition to the flexural cracks, there will be possibility of punching failure, okay, or punching of this footing. The colorman may try to punch this part of the footing. So once we know this, we may provide the adequate thickness of the footing so that the punching may not proceed with it to the bottom, and the flexure will be resisted by maybe reinforcements and so on. Okay, so that's why we need to know the structure load response. There is structure, there is load, so and there is a response. Once we know this, we can provide a safe, adequate, economic reinforced concrete element. Okay, if I go to the third part of this lesson, we will go to why do we use, or why do we need to use, the reinforced concrete. What makes it different from the other materials is what we will explain and discuss it here. So we said that for a beam with such arrangement, okay, and such a loading, such a deformation, the response will be like this. Okay, and we will and accordingly, if we have such kind of maybe neutral axis that is around here, around the section, okay, at the around the midsection of this element, okay, it may not actually be at the center, but however it is within the cross section most of the time for the beams. Okay, now there will be tensile stress below this neutral axis, and there will be compression at the top of this neutral axis, and as a result we are expecting tension cracks around the bottom. Basically we call it flexural cracks. Okay, and the top part is concrete, and concrete has a property that makes it good to withstand compressive stresses. So if you have such a behavior in so many conditions of the beam and maybe other reinforced concrete elements, we need to understand the properties of the concrete and the reinforcement so that each one is placed according to where it is required. Okay, now we know that we have concrete and we have reinforcement. So concrete has its own qualities and weaknesses, and reinforcement has also too. And concrete, for example, has a good qualities for resistance to corrosion and resistance to fire. Okay, good in compression and formability. You can cast concrete in different shapes, okay, as you want, maybe circular, maybe rectangular, whatever, and it's durable. Okay, it can withstand loads for a very long period of time. Okay, so these are the good qualities, and others, okay, and others which are not mentioned here are some of the good qualities of the concrete. Whereas in weakness, we can describe that concrete is weak in tension, okay, and it has a brittle behavior. Okay, so after the yield it will not have that much capacity to deform, and as a result it will fail, okay, in tension easily. Okay, but in compression it's good. If you come to the reinforcement side, weaknesses can be described as its susceptibility to corrosion. Okay, so reinforcements are easily attacked by corrosion from the environment and moisture and related things. Okay, and maybe other chemical attacks, and it's easy to corrode, and it's weak in fire, because we know that when you want to make something from metals, you need to fire it and you need to heat it. Okay, so after heating it becomes weak so that you can form it in different shapes. Okay, so it's weak in fire. Okay, and some of the good qualities are that it has got a very high tensile capacity, and it is very ductile material, and its compressive strength is also similar to the tensile capacity. However, this is provided that the lateral deformation or buckling are restrained. Okay, if lateral buckling are restrained, we are expecting that the reinforcement will have the same quality in compressive strength as the tensile capacity. Now when we add these two materials, reinforcement and concrete, we get reinforced concrete. We are expecting to eliminate the weaknesses of each material by the strength of the other material. For example, here the quality will eliminate the weakness, and the quality here will eliminate the weakness. What do you mean by that? For example, here we have corrosion resistant concrete, and here it is the reinforcement is weak and susceptible to corrosion. So if we cover it with concrete, it means that we are going to get corrosion resistant structure. And this says it is weak in fire, the reinforcement. If we cover it with concrete, the concrete will protect it from the fire to some degree, and we are going to get a fire resistant material to a satisfactory level. And here it is weak in tension, the concrete, and reinforcement has got high tensile capacity. So we are going to eliminate that by providing reinforcement in the tension zones. And we said that it's brittle here, and the reinforcement is ductile, so the ductility of the reinforcement will support the concrete so that the overall section will become ductile at some level. Okay, so to some degree of ductility for the section will be achieved by the reinforced concrete. So at last, after the weaknesses are removed, we are going to get qualities plus qualities. A material that is corrosion resistant, fire resistant, high compressive strength, high tensile strength, formability, durability, and ductility. Okay, these all qualities will be the result of adding the reinforcement to the concrete. Okay, so that's why we need to provide reinforcement in the concrete. And here we can summarize our conclusion. It is to utilize the best property of each material and to get a very strong, economical, and user-friendly, because it will be user-friendly as we can create different forms and shapes from the reinforced concrete. Now, if we have such a beam and with such a loading, we said that such a cracks will surely occur. As a result, since we know that concrete is weak in tension and it will go cracking around the bottom in the tension zone, because we said the top part will be under compression, that the bottom part will be under tension, reinforcement will be required to be provided at the bottom so that the tension crack does not occur, and shear failures will be eliminated or minimized by providing the stirrups with certain spacing as required. Again, here for the continuous beam, here there will be tension crack at the bottom and here around the support at the top. Then we will provide reinforcement here to resist the bottom crack, again here at the bottom to resist the bottom crack, and at the top here to resist the top flexural cracks. And for the shear, we are going to provide the stirrups. So here, this is what we call it systematic provision of reinforcement, so that we get reinforced concrete result. Okay, the base of the reinforced concrete result will be by providing reinforcement as required in the required places. Okay, again, finally, if we come to the footing, we said that pinching will occur. Pinching will be resisted by providing appropriate thickness, and the flexure will be provided resisted by providing reinforcement around the tensile zone. Okay, so this is basically how structure load response, understanding the structure load response and understanding the material properties of each material will give us the skill and the knowledge to use the materials in a very professional way and as required. Okay, as required, systematically as required. So this is how you will use the reinforcement and the concrete accordingly. Let's do this simple exercise. If you have such a bridge, okay, you have such a deck, concrete deck maybe, and you have such kind of cables, maybe possible, okay, such kind of vertical members, and such kind of arch. Our arc is somewhere here. Now, how do you think the structure load response will be? You may pause the video and take a break and see this picture to try to understand it. Okay, well, the loads will be the dead load of the element and the live load, maybe vehicles, whatever it's. Okay, so the load will be resting on this deck, but this load will be transferred through these cables to the top part. This is the arc part. Okay, the arc may be concrete, maybe steel, whatever it is. Now we know that these vertical members are supporting or are suffering tensile stresses. So we surely need to provide a material that is strong in tension. Okay, so you may need to provide cables, tension cables, or high yield strength cables. Okay, so as an engineer, I may not provide concrete here. Okay, because concrete is weak in tension, you need to provide maybe tensile resisting cables. So this is how you will design it. Now the load will come to here and it will go through this central line of the arc. So mostly we are expecting that this is under compression. The load is under, the element is under compression. So this part may be made from concrete and reinforced with some reinforcement because it is basically suffering compression stresses. So knowing the load response of the element, you can provide the elements to be economical and a systematic way. And the bottom part, after the load has been transferred from the deck to the arc and from the arc to the supporter around here, this inclined force will be will have components in the vertical as well as in the horizontal. Okay, now if the horizontal component effect is very large, it means that this deck will surely suffer tension force. Okay, so it may not bend like we said in the simply supported beam, because this beam or this deck has got cables at some interval that will transfer the dead and the live load from the deck to the top arc. Okay, so for this, the bending due to the loads may be very small. However, finally the load comes here. If the horizontal component is very large, this whole component, the deck part, will be under high tension. So as a designer, we need to provide this concrete deck with appropriate reinforcement so that the cracks will be eliminated in the concrete. So here we said these are under tension, so tension cables may be provided. These are under compression, maybe some reinforced concrete will be provided, and maybe at the bottom here you have some member under tension with a very small bendings, so you may provide reinforced concrete, ensuring that tension cracks will not occur. So this is what we call it a systematic design of reinforced concrete. Now the same scenario, but with a little bit change. The arc that was at the top now is at the bottom. Now the loads are here, as we said. This load will be transferred through these members. Now these members that was here, they were under tension. However, here it is under compression. So maybe reinforced concrete columns may be used, or piers, or maybe walls can be used, so that the loads will be transferred to from the deck through these vertical members under compression to these arcs. So this arc will finally transfer the load to the end supporting members. Okay, so these are now a compression members. So the compression members, you may use reinforced concrete element, maybe masonry work, and so on. Okay, so this is what we say: understanding the structure load response and the material properties of different civil engineering materials. This will lead you to design a structure that is adequate and safe. Okay, finally, if we come to the last part, that is the fourth part, we need to understand the materials under the reinforced concrete. Basically, we said reinforcement and concrete. So concrete and reinforcement have their own ultimate capacity. That will be found using tests. Okay, using tests, you will get the maximum capacities of these materials. Now, if I start with the concrete, as per the Eurocode and as per the ESEN, the same table 3.1, okay, they show us that the concrete are indicated or labeled using this kind of indexing. Okay, for example, concrete C20 by 25. Previously, they were used to be called C25. However, now C20 by 25. This has got representations. Now 20 stands for FCK, and FCK means the cylindrical strength of the concrete, the characteristic cylindrical strength of the concrete, and this is the characteristic cubical strength of the concrete. Now, for example, if somebody says to you C20 by 25, he is indicating to this part. This is FCK 20, FC cubed is 25. So 20 by 25 means this grade. Okay. Similarly, another example, If you have C25 by 30, FECK is 25 and FEC cube is 30, you come here 25 by 30. Understand? So this is how we will directly read the cylindrical strength and the cubical strength, and if there are other properties related to each grade, for example, FECM is 33, FECTM is this, and accordingly you will continue to the last. Maybe additional data that you may need, maybe the modulus of elasticities. If you are designing using softwares such as ETABS or so on, you will need to provide the modulus of elasticity. However, the latest versions of ETABS are automatic, and they will provide this data automatically. Okay, when you select the appropriate grade of the concrete, they will give you this. However, for example, now ECM, this is the modulus of elasticity of the concrete, they are provided here. Okay, they are provided here. So for each grade of the concrete, there will be the respective modulus of elasticity. Okay, now we know that we said that there is the ultimate capacity of the concrete. However, we will use not the ultimate but the design strength. These design strengths are found by providing certain factors and the factor of safeties. Okay, now the design strength FCD is found by this formula, where alpha cc and gamma c is given as follows. For example, gamma c is given in table 2.1n here. Okay, for these two situations, that is persistent and transient situation. And what's persistent situation is the normal use of the structure, whether it is a school, whether it is a hospital, whether it is other complex structure. The normal use of the concrete is considered as persistent condition. And the other is the transient situation. The transient situation is such a situation such as when you are doing the repair or the maintenance of the structure or during the construction. These two conditions are called the transient situation. So in the persistent and the transient situation, the factor of safety is just 1.5. However, if you are considering accidental situations such as maybe where there is explosion, where there is fire, where there is impact, such situations are called accidental, and you may need to consider a lower factor of safety, that is 1.2 for the concrete. Okay, 1.2. What about alpha cc? It's a factor that takes into consideration the long-term effect on the tensile strength. Okay, now this factor is given to be 0.85 in the Ethiopian code and as 1 as per the Euro code 1992, and this 1992. So which one gives us a more safe or a more conservative result? It is the Ethiopian code that gives a better a more conservative result. Okay, so providing this will give us FECD that is less. So designing my concrete, my structure, assuming a lower strength, will result in a more safe structure. Okay, so for this one shows or gives a better or a more conservative result. Okay, if I go to the steel parts as per the two codes are given. This is the stress-strain relationship given in the two codes. This is for hot rolled steel and this is for cold worked steel. Okay, the reinforcements are generally under the hot rolled steel. Okay, however, this is can also be used for the steel sections. Okay, structural steel sections such as maybe angle iron, maybe C sections, and maybe others. Okay, now the yield strength that is considered in the Ethiopian as well as the Euro code is the steel that has a specified steel strength of between 400 to 600 megapascal only, not less, not more than this. Okay, so your reinforcement FYK must lie between these two limits. Okay, these two limits. There is a very important point that you should consider. We talked about ductility in the previous slides. However, what's ductility? It is the ability of material to sustain a large deformation. Okay, large permanent deformation after the yielding. Okay, until fracturing. Okay, now here the reinforcement when stressed, it will have certain stress and a certain strain. Finally, after it yields, okay, after it yields, if from the yield up to the fracture, if the strain is significant or large, we call it ductile. If, however, after the yield it fails, we will not call it ductile, it's brittle. However, it may have a lower ductility, maybe a medium ductility, maybe high ductility property, okay? So this is what we call it ductility. Ductility is basically the ability to sustain large deformation, okay? Large permanent deformations. Now, this is the zone that is covered under the strain and the stress curve, okay? The stress strain curve. This is the safe zone, okay? If your section lies in between this zone, it may be safe, okay? It may be safe. However, for design purpose, we cannot use this. We will use the design strength of the material. Now, this is the graph, and here you have the strain, okay? From this 0 and up to the maximum strain, okay? Up to the maximum strain. For the cold worked, it shows a relatively less ductile material, okay? Less ductile material. Now, if we deal with the hot rolled one, this graph can be simplified by these two straight lines that connects the 0 to the yield, from the yield to the final ultimate capacity of the section. This is what we represented here. We call it the idealized graph, okay? The idealized graph. However, this idealized graph must be divided by some factor of safety so that we design or we get a material that is okay and that can give us a safe result, okay? Now, if we divide this curve by factor of safety, we will go down by some level, by some distance, go down somewhere here, okay? Now, for the design purpose, this curve can be used, okay, or this curve can be used. However, since we generally use the FYD for the design purpose, this horizontal part will give us a satisfactory result and a more safe result, okay, more conservative result. And here the reinforcement may be able to go up to this much strain, epsilon UK. However, we will use a design strain and we will make sure that the section may not go beyond this much strain, okay? Now, as a result, this yellow shaded region may give us a safe result. However, for design purpose, this green shaded element zone will be the section that our sections should lie within, okay? Okay, now we said according to the ductility, reinforcements are categorized into 3. Even though you may categorize the reinforcements according to their diameter, maybe 5.6, 5.8, 5.10, and so on, 5.20. However, generally, reinforcements are classified based on ductility into these 3 classes: Class A, Class B, Class C. Class A are those reinforcements that have the lowest ductility category. Usually, these are associated with the reinforcements with less than or equal to 12 mm diameter. Okay, so such kind of rebars are used where the ductility requirement is very low or not significant. For example, ground floor slabs that lie on the ground where there is no bending and such things, you may provide such kind of reinforcements with very low ductility. And there is Class B that shows a medium ductility. These are the commonly used one. The generally used type of reinforcement in most of our structures are Class B reinforcements. Finally, Class C are those that has or that possess the highest ductility. Such reinforcements are needed in the earthquake or in the seismic zones. So reinforcement must have the adequate ductility so that when the earthquake hits, it will deform but should not fail. Okay, should not fail. So these 3 categories of reinforcements are given in the Euro code as well as in the Ethiopian code. Now, if I return back to the graph of the reinforcement, you see that you have the yield stress here, the yield strength, you can say. Here, the design strength, which is the yield divided, the characteristic yield strength divided by some factor of safety, then you get the design strength. Similarly here, this is the final ultimate capacity of the reinforcement. So you have these 4 points. This point, this point, this point, and this point. These are the points that ETAP software or sub software will ask you to enter. So this is FYK divided by factor of safety gamma S, you get this. Now if you multiply this with a factor K, you get this point, and if you multiply this point with a factor K, you get this point. Now what's this K? This K is given in the code, in the Annex C of both code, the Ethiopian and the Euro code. These are the classes A, B, C. Now when we deal with the ductility that we were talking about, class A possesses this much ductility, around 2.5, whereas in the B class we have this much ductility, 5%, and we have in the class very high ductility that is greater than or equal to 7.5. This is greater than or equal to 5, where the K value that I have been talking about is given here. K equals for class A around or greater than or equal to 1.05. For class B, that is the generally used one, it is 1.08. Okay, around 1.08. So it's greater than or equal to 1.08. So you can use 1.08 or 1.09 or maybe 1.1. So around there. Okay, you can play around that that value. For class C, you may use these factors. Okay, K factors for this. Okay, now we have talked about the ultimate strength of the reinforcement. Okay, we need to provide the design strength of the reinforcement. So the design strength of the reinforcement is calculated by FYK divided by gamma S, as we said earlier, where gamma S can be found from this table as we did for the concrete. For the persistent and transient, I will use 1.15, and for the accidental situation, you can use 1.0. So the yield strength will be this divided by the factor of safety gamma S, which can be read from this table. Well, that's all for this lesson. Thank you. If you have any questions, you can write in the comment box, or you can directly text me through my Telegram. Thank you. See you next time.